Welcome back to Decentralized Application Development Crashcasts. I'm Sheila, and if you're enjoying our podcast, please take a moment to rate us on your favorite podcast platform. It really helps us reach more developers like you. Today we're diving into Chapter 4 of our first season, focusing on decentralized storage systems. Victor, are you ready to talk about consistency models?
Absolutely, Sheila. I'm excited to explore this crucial aspect of distributed systems. Before we dive in, let's kick things off with a quiz question for our listeners. Are you ready?
Go for it, Victor. I'm sure our listeners are eager to test their knowledge.
All right, here's the question. In which consistency model would you be more likely to encounter a scenario where two users reading the same data at the same time might see different values?
Ooh, that's an intriguing question. It really makes you think about how data behaves in distributed systems. I'm curious to see how our listeners will approach this. Victor, why don't you break it down a bit for our audience?
Certainly. This question touches on the core of what consistency models are all about. It's asking our listeners to consider how data updates spread through a system and what guarantees different models provide. Without giving away the answer, it's worth thinking about how real-world applications like social media feeds or collaborative document editing might handle such scenarios.
That's a great way to frame it, Victor. Now, before we dive deeper, let's make sure our listeners are on the same page. Can you give us a quick definition of what we mean by consistency in the context of distributed systems?
Absolutely. In distributed systems, consistency refers to how and when updates to data become visible to different parts of the system. It's about ensuring that all nodes or clients see a coherent and agreed-upon view of the data, despite the challenges of spreading information across multiple machines or locations.
That makes sense. So it's like making sure everyone's reading from the same page, even if they're in different rooms, right?
That's a great analogy, Sheila. Now let's start with one of the main consistency models, strong consistency. Can you tell me what you understand about this model?
Well, from what I know, strong consistency seems to be the most straightforward model. I think it means that once a write operation is completed, all subsequent read operations will return the updated value. Is that correct?
You're on the right track, Sheila. Strong consistency indeed provides that guarantee. It ensures that all clients see the same data at the same time, regardless of which node they connect to. It's like having a single authoritative copy of the data that everyone reads from and writes to simultaneously.
That sounds ideal. Why wouldn't we always use strong consistency then?
Great question. While strong consistency provides the most intuitive behavior, it comes with trade-offs. It often requires synchronous communication between nodes, which can lead to higher latency, especially in geographically distributed systems. It can also reduce availability if some nodes are unreachable. This is where the CAP theorem comes into play, which states that in a distributed system, you can only have 2 out of 3: consistency, availability, and partition tolerance. We'll discuss this in more detail later.
I see. So there must be alternatives that address these limitations, right?
Exactly. This brings us to our next model, eventual consistency. In this model, the system guarantees that if no new updates are made to a given data item, eventually all accesses to that item will return the last updated value. However, different replicas might temporarily have different values for the same data.
That's interesting. So it's like if I tell a piece of gossip to a few friends and they pass it on to others. Eventually everyone will hear the same story. But for a while, some people might have outdated or incomplete information.
That's an excellent analogy, Sheila. Eventual consistency is indeed very much like gossip propagation. It allows for temporary inconsistencies but guarantees that the system will converge to a consistent state over time.
I can see how that might be useful in certain scenarios. Can you give us some real-world examples of where each of these models might be used?
Certainly. Strong consistency is often used in systems where immediate accuracy is crucial, like financial transactions or inventory management. You wouldn't want 2 people to book the last seat on a flight, for instance. Eventual consistency, on the other hand, is commonly used in systems where some delay is acceptable, like social media updates or collaborative document editing. Think of how your Facebook feed might not show a new post immediately, but it will appear eventually.
That makes a lot of sense. It seems like the choice between these models really depends on the specific needs of the application. Are there any common misunderstandings or pitfalls developers should be aware of when working with these consistency models?
Absolutely, Sheila. One common misconception is that eventual consistency means no consistency. In reality, it provides a different set of guarantees. Another pitfall is overestimating the need for strong consistency, which can lead to unnecessarily complex and slow systems. It's crucial to carefully analyze your application's requirements and choose the appropriate model.
Those are great points, Victor. Before we wrap up, do you have any interesting facts or anecdotes about consistency models you'd like to share?
Here's a fun fact. The idea of eventual consistency was actually inspired by how DNS, domain name system, works. DNS uses a hierarchical naming system and caching, which allows for temporary inconsistencies, but eventually converges to a consistent state across the internet. It's a great example of how eventual consistency can work at a global scale.
That's fascinating. Now, I think it's time to reveal the answer to our quiz question. Victor, would you like to do the honors?
Of course. The scenario where two users reading the same data at the same time might see different values is more likely to occur in an eventual consistency model. In strong consistency, all reads would return the same value, but eventual consistency allows for temporary discrepancies as updates propagate through the system.
Thank you, Victor. To summarize today's episode, we've learned about two main consistency models in distributed systems: strong consistency and eventual consistency. Strong consistency provides immediate, system-wide consistency, but can impact performance and availability. Eventual consistency allows for temporary inconsistencies, but guarantees convergence over time, offering better performance and availability in many scenarios. The choice between these models depends on the specific requirements of your application.
Excellent summary, Sheila. Remember, listeners, understanding these consistency models is crucial for designing efficient and reliable decentralized applications. In our next episode, we'll dive deeper into the CAP theorem and how it relates to these consistency models in the context of distributed systems.
That's all for today, folks. If you found this episode helpful, please visit crashcasts.com, join our Discord community, or support us on Patreon. Don't forget to subscribe and rate our podcast. Your support means the world to us. Until next time, happy coding.